This is Daryl with Cisco Hands-On Training. It's the 7th of March 2009, and today we're going to talk about rapid spanning tree. And I'm happy to say that we're almost done with our switching episodes, and then we get to move on to some interesting design stuff. The website is ciscohandsontraining.com. Diagram will be on the website in the comments. In iTunes, search on Cisco Podcast to find this podcast. I always appreciate links. And I've completed remastering all old episodes that they work on the 5th generation iPods and including the iPhone. And that's good news, but unfortunately some of the older episodes are out of order in the podcast directory, which is a little bit inconvenient for people, and I'll try to fix that, but unfortunately every time I fix that, it just gets it more out of order. Okay, so let's talk about spanning tree. We previously learned about the historic 802.1d spanning tree. An 802.1d spanning tree is based on timers. The root bridge would send out a BPDU every 2 seconds, and they would propagate down the tree of your environment. So each switch in the environment would not originate BPDUs. Instead, they would just pass on the BPDUs that they receive. So if you fail to receive a BPDU from a upstream neighbor, if you're a switch and you fail to receive a BPDU from an upstream neighbor, there are two possible causes. One is that your link to the upstream neighbor died, and the other is that the link from that upstream neighbor died somewhere, and you don't know where. And so you have to slowly reconverge because you don't want to create a bridging loop while you're reconverging. So that's why spanning tree reconvergence is so slow. The first thing is you wait for 20 seconds for max age to time out before you even decide that you've had some sort of failure. And then you go through the listening and learning states, which can be another 30 seconds before you actually reroute around the failure. Rapid spanning tree is rapid spanning tree is based on hellos and triggered updates. So each bridge in a rapid spanning tree environment will send hellos every 2 seconds out the other links, regardless of receiving BPDUs from an upstream neighbor. So if you fail to receive BPDUs for, let's say, 6 seconds from a neighbor, which is 3 times the hello interval, then in rapid spanning tree you'll decide that either the neighbor's down or your link to the neighbor is disconnected at some point, and you can immediately act on it. You don't need to guess whether it's the link to the neighbor or some link higher up in the stream. So rapid spanning tree can more rapidly detect that a failure has occurred because it detects it after 6 seconds, and it knows that the failure is between you and the neighbor or the neighbor itself. Now the old spanning tree has port states disabled, listening, learning, blocking, forwarding. The port states are simplified in rapid spanning tree. They are discarding, learning, and forwarding. Here's a URL. It's the page on Cisco called the Understanding Rapid Spanning Tree Protocol, and I use that when preparing for this. Port roles in rapid spanning tree are slightly different. You still have the root port, which is the port which goes towards the root. So in this topology, if the switch 1 had the lowest priority, that means it's become the root. So on switch 3, fast Ethernet 0/1 would be the root port. On switch 2, fast Ethernet 0/1 would be the root port. You have the designated port. Each segment has a designated port, which is the port closest to the root bridge. So in this environment, we have 1, 2, 3, 4 segments, and so we have 1, 2, 3, 4 designated ports. On the root bridge, every port is a designated port. And then out here on this segment between switch 2 and switch 3, the designated port will either be the one on switch 2 or it'll be the one on switch 3. And typically, because the bridge 2 has a lower priority than bridge 3, because we set it as a spanning tree backup route, the designated port for the segment will be fast Ethernet 0/3. You have an alternate port, which is a uplink fast has basically been included in rapid spanning tree. So you don't even need to include, you don't even need to configure uplink fast anymore. Rapid spanning tree does it for you automatically. And so in this environment, fast Ethernet 0/1 will be the root port, and fast Ethernet 0/2 will be the alternate port. You also have something called the backup port in rapid spanning tree. If you have two connections to the same segment, then you will, if you have two connections to the same segment, then one of them will be the backup port. And that's pretty rare, but like if you had a switch and you had two connections going to the same hub or something like that, one would be your designated port and the other one would be a backup port. Okay, so rapid spanning tree, the bridges send BPDUs every hello time, and they all send BPDUs to each other. So every bridge will send BPDUs out each port that can go to another. Yeah, every bridge will send out BPDUs every 2 seconds out every port, and the 3 missed BPDUs, which is normally 6 seconds, means the connection to an immediate neighbor is down. But most of the time you detect it even faster than that. If this link physically goes down, then the switch is going to detect it immediately. So if the link physically goes down, you don't even need to wait for the 6 seconds. Now, an edge port is a port that goes to an end host. So there's no possibility of a loop. And how does a switch know if a port is an edge port? Well, it knows if a port is an edge port if you have portfast configured on it. So we could configure fast Ethernet 0/1 going to this router as an edge port because it would, because the router is not running spanning tree, of course, it's not bridging, and so there's no possibility of a bridging loop through it, so you just always forward right away. Now, one thing that I have not talked about previously is something called the topology change notification. A topology change notification BPDU is another type of BPDU, and it's basically an alert that something has changed in your environment. So if fast Ethernet 0/2 went down or came back up, then switch 3 would generate a topology change notification BPDU, send that up to the root bridge, and the root bridge would disseminate the BPDUs with the topology change notification flag through the entire environment. The effect of the topology change notification BPDU is that each switch in the environment will age out their MAC address table quickly. Now, why would you age out a MAC address table quickly? Because the topology has changed. So the port that you might need to forward to get to a particular MAC address might have changed. So waiting 5 minutes for your normal MAC address table timeout to occur could mean that you'd lose connectivity to a particular host for up to 5 minutes. So the topology change notifications will cause the MAC address tables to age out faster, which has the benefit of fixing connectivity faster if you have some MAC address table entries going what is now an invalid path. But it has a disadvantage, and the disadvantage is that the topology change notifications causing the MAC address table to time out could cause more flooding in your network, because if you receive an Ethernet frame with a destination MAC address which is not in your MAC address table, you will flood it out all your ports. Now, in rapid spanning tree, we just defined what an edge port is. An edge port is a port that you configure portfast on, and rapid spanning tree knows that cannot possibly go to another switch. Now, if a edge port goes down or up, in that case, you will no longer send a topology change notification with rapid spanning tree. So configuring edge ports configuring portfast has multiple benefits now. When when a connection to a host is coming up, you don't need to wait, the old spanning tree, 30 seconds for it to for the port to be activated. And in addition, you no longer send topology change notifications, which can cause flooding, more flooding. You only need to send topology change notifications if links between switches go down, which actually makes sense, because if a link between a switch goes down while it's topology change, then you'd send a topology change notification. Okay, so 3 missed BPDUs means that the connection to the immediate neighbor is down. We know it's the connection to the immediate neighbor because every switch is sending BPDUs to every other switch every 2 seconds. The spanning tree portfast makes a port and edge port. Edge ports going down and up do not result in topology change notification BPDUs. Link type. Rapid spanning tree has 2 link types. One is point-to-point and one is shared. Now, Ethernet can be a shared medium. I mean, that was originally designed as a bus. People don't generally run it as a bus anymore. Most links today run as point-to-point full duplex links. So you know that there's only 2 port hosts on a segment. But it's possible in Ethernet to have a segment with more than 2 hosts on it, and especially if you're using the older bus technology. So because of that, because of that, rapid spanning tree protocol has to be able to deal with that situation. So full duplex links are automatically determined to be point-to-point, and rapid spanning tree converges more quickly through point-to-point links. Half duplex links are designated as shared links, and rapid spanning tree has to deal with the possibility of multiple hosts on that link, and unfortunately that means that rapid spanning tree goes slower through that link. Okay, we've been talking about rapid spanning tree for a bit here, but what exactly makes rapid spanning tree different? What makes rapid spanning tree different is that you no longer wait for timers to run out in order to reconverge. In normal spanning tree, your root bridges send BPDUs out the port, and you wait for listening and learning times before you start forwarding. That's timer based. In rapid spanning tree, the way you reconverge is that is due to triggered updates. Switch 1 knows that a change has occurred and will immediately talk to switch 2 and switch 3 to figure it out. Switch 2 and switch 3 will talk to any of their neighbors to figure out how to set up the new topology, and they'll immediately talk back. No timers. Everything is triggered. That's why it's fast. How exactly does it work? Well, let's say that the link between switch 1 and switch 3 is down. And so in our topology, with this link down, fast Ethernet 0/2 is a designated port. Fast Ethernet 0/1 is a root port, because switch 1 is our root bridge, because we configured it that way. And then over here on this segment, fast Ethernet 0/3 is designated for the segment. Fast Ethernet 0/2 is the root port for switch 3. And of course, this segment here between switch 1 and switch 3 is down. Let's say we bring up switch 1 and switch 3. Well, switch 1 and switch 3 come up, and they're going to start talking to each other via BPDUs, and switch 3 is going to quickly figure out that it needs to make fast Ethernet 0/1 a root port, and switch 1 is going to quickly figure out that it needs to make fast Ethernet 0/3 a designated port. Now, normally, to avoid a loop, what you would do is you would wait 30 seconds for the BPDUs to go elsewhere in the environment and result in blocking on another port. That's 802.1d. But with rapid spanning tree, what you do is when the ports come up, they start out in the discarding state, and then the switch 1 is going to send a proposal to the downstream switch saying, I want to make this port designated. And the downstream switch is going to, what it's going to do is it's going to prevent a loop by putting fast Ethernet, by putting all other ports other than edge ports in the discarding state. And then switch 3 is going to agree to the proposal, and then fast Ethernet 0/3 will immediately become the designated port. Fast Ethernet 0/1 will immediately become the root port, and they'll immediately go to the forwarding state. Okay, great. That shows how the link between switch 1 and switch 3 can come up quickly, but what else just happened? To prevent the loop, switch 3 put fast Ethernet 0/2 into the discarding state immediately. Now what switch 3 will do is it'll talk BPDUs with switch 2, and it'll say, they'll figure out that fast Ethernet 0/3 needs to become a fast Ethernet 0/3 needs to become a designated port, and fast Ethernet 0/2 needs to become a discarding port, actually, in that case. So since switch 3 knows that fast Ethernet 0/2 becomes a discarding port, it would just continue to discard on that port and you'd be done. Now let's say that switch 3 had a higher priority than switch 2. Then switch 3 would say, hey, fast Ethernet 0/2 should become a root port, and fast Ethernet 0/3 should become a designated port. I'm sorry, fast Ethernet 0/2 would be designated, and fast Ethernet 0/3 would be root in that case if switch 3 had a lower priority than switch 2, meaning that switch 3 is the way to get to the root bridge. So in that case, switch 3 would then send a proposal to switch 2 saying, let's start forwarding here. Switch 2 would do something called the same thing called sync, which is block on or put every other port that's not an edge port into discarding mode and then accept the proposal. Eventually you get down to the bottom of the tree where the ports that the switch put into blocking or discarding state are supposed to be in discarding state in your in your final topology. So you're done. Now you notice the one thing that didn't happen there was no timer. So switch 1 sends a proposal to switch 3 discards and everything else and accepts to prevent a loop and accepts the proposal on switch 1. Then switch 3 on each of those ports that we're now discarding, it sends a proposal out, and switch 2 blocks on everything else and or discards and everything else and accepts the proposal. And then you're done, because if the priority on switch 3 is lower than switch 2, then fast Ethernet 0/1 discarding is your final state that you're supposed to be in. No timers. You don't have to wait, and that's why rapid spanning tree is so fast. Let's see an example. So I have some debugs enabled here. So show debug. I've got debug spanning tree general, spanning tree debug event, spanning tree debug spanning tree root, debug spanning tree state change, debug spanning tree pvst plus, and debug spanning tree uplink fast enabled on all 3 of my switches. So let's go ahead and conft int fast 0/2. So I'm going to take the link between switch 1 and switch 2, and I'm going to shut it. And you can see I can ping switch 3 what I'd expect. Now let me do a no shut and see what happens. Okay, well I'd left my port between switch 1 and switch 2 physically unplugged while I was practicing, so I just plugged it back in, and let's look at the log messages. Fast Ethernet 0/2, so here I am on switch 1, fast Ethernet 0/2 changed state to up, and then it created, it put it into the spanning tree instance, and created it in spanning tree, and then it initialized the port, and then it realized 1 second later after it came up that it needed to go in a designated port. And so it transmitted a proposal to the switch on the other side, and then the switch on the other side, it transmitted a proposal and it received an agreement 1 second later. And because it received an agreement, it sent. It doesn't actually say it here, but it went immediately into forwarding state. Let's go ahead and look at the logs on switch 2 during that time. And spanning tree fast Ethernet 0/1. It fast Ethernet 0/1 changed state to up. It initialized it in spanning tree, and it went. It was going to go designated. It transmitted a proposal, but it received a superior BPDU from the remote side. So switch 2 was trying to put fast Ethernet 0/1 into designated port mode, but it received a superior BPDU from switch 1, so it realized that it should make fast Ethernet 0/1 a root port. So fast Ethernet 0/1 became a root port, and because it became a root port, it blocked fast Ethernet 0/3. And then fast Ethernet 0/3 needed to become designated, so it immediately sent a proposal on fast Ethernet 0/3. And once it sent a proposal on fast Ethernet 0/3, it received an agreement from the other side. So you can see how fast that worked. The port came up, changed state to up, at 16 seconds after the minute. And by 18, that was fast Ethernet 0/1, and by 18 seconds after the minute, in 2 seconds, in less than 2 seconds, switch 2 realized that fast Ethernet 0/1 needed to become a root port, made it a root port, realized fast Ethernet 0/3 needed to become a designated port, requested, sent a proposal to switch 3, received an agreement, and started forwarding. So that is why rapid spanning tree is so rapid, because it doesn't wait for any timeouts. It sends proposals and it immediately receives agreements. And then here it says it's sending a proposal on fast Ethernet 0/3. That's every 2 seconds it sends a BPDU. Seems like it stopped after a while. I think that's just hold on for a second. I'm not sure why those log messages are saying just that, but I do know that they're going to switch 2 and switch 3 are going to send BPDUs to each other every 2 seconds. Okay, so let's unplug that port and see it again. Actually, conf t int fast 0/2 shut. So we shut down the port and it deleted it in the spanning tree. Let's switch. What switch 2 did was more interesting. So the root port went down. It realized we want to become the root port. We want to become the root bridge. It deleted these because it lost its only root port, and then it realized it received a superior BPDU from switch 3, which is actually it received the superior BPDU from switch 3, but it's actually switch 3 sending out BPDUs saying that switch 1 is the root bridge, and with switch 1's priority, switch 2 recognizes that as superior. So fast Ethernet 0/3 to switch 3 became the root port, and we were immediately synced because that's upstream. And so we started forwarding on that. So again, the port went down at 20 seconds after the minute, and we figured out at 20 seconds after the minute that we need to start forwarding out fast Ethernet 0/3. Meanwhile, on switch 3, when the link between switch 1 and switch 2 went down, switch 2 tried to become the root bridge for a second, and switch 2 sent a BPDU to switch 3, and then switch 3 sent a update, the superior BPDU out fast Ethernet 0/2, and made fast Ethernet 0/2 designated, and sent a proposal on fast Ethernet 0/2 and received an agreement from switch 2 almost immediately afterwards, and went into forwarding state. So again, to review, a new link comes up. Let me go back to switch 1, and let's just look at this again, because this is important. Rapid spanning tree is what everybody's using these days. Int fast 0/2 no shut. Fast Ethernet 0/2, we no shut it, so spanning tree starts running on fast Ethernet 0/2, and it becomes a designated port because we're the root bridge, so all of our ports are designated. So we transmit a proposal on fast Ethernet 0/2, and we transmit a proposal on fast Ethernet 0/2, and we receive an agreement 1 second later, and we're done converging. Meanwhile, on switch 2, fast Ethernet 0/1 changed state to up. Fast Ethernet 0/1 sent a proposal to us. We agreed to it and sent an agreement immediately. And meanwhile, fast Ethernet, or switch 3, we received a BPDU from fast Ethernet 0/2. Not sure why it's exactly saying role superior BPDU, but we received a BPDU. Fast Ethernet 0/2 became an alternate port as opposed to previously when it was a forwarding port. All in a fraction of a second. Okay, other note, okay, so rapid spanning tree, new link comes up, which would cause a port to become designated. So the upstream switch, which is closest to the root bridge, would become designated. The downstream switch, which is furthest from the root bridge, would become a new root port. The new ports go into the discarding state. The upstream switch sends a proposal to the downstream switch. The downstream switch sets discarding on all other designated ports, and that's called sync. And then once it's discarding on all the other ports, except edge ports, the downstream switch agrees to the proposal, at which point the upstream switch and downstream switch start forwarding on those ports. And then the downstream switch repeats the process, sending a proposal out to each further downstream switch, and that's why it recovers so quickly, because there's no timers. Now, there are ports that won't respond to rapid spanning tree. Two examples are rapid spanning tree, are switches running the old spanning tree protocol because they don't understand the new spanning tree protocol. If you receive BPDUs on a port in the old format, then a rapid spanning tree switch will run in a compatibility mode, which means it'll still run the old protocol, which means it'll just send BPDUs every 2 seconds, and there will be a 30-second delay until those ports go forwarding. So it's important when you're running rapid spanning tree to try to migrate an entire environment, an entire layer 2 domain. You don't want to have some switches running rapid spanning tree and some switches running old spanning tree, because then you'll get the old spanning tree convergence. And then rapid spanning tree obsoletes backbone fast. If you remember, backbone fast was a protocol where switches talk to each other to detect link failures. Well, rapid spanning tree is exactly the same thing. It's a protocol where switches are talking to each other, and it's even smarter. Uplink fast still works, but is automatically built in. Rapid spanning tree automatically detects the existence of alternate ports and backup ports, and will forward them more rapidly when appropriate. Portfast, BPDU guard, root guard, and loop guard are still useful and can still be enabled in rapid spanning tree. And in fact, portfast is essential, because portfast is essential for creating edge ports. Let's look at that. So, show spanning tree. I only have one VLAN in my environment, and you can see that fast Ethernet 0/1 on switch 1, which goes to my router, is a shared port. Why is it a shared port? It's a shared port because that port is half duplex. Half duplex ports are always shared. And if I make it full duplex, conf t and fast 0/1 duplex full, show spanning tree. So now that I made fast Ethernet 0/1 full duplex, it's a point-to-point connection. But actually making it a full duplex in this case was a mistake, because the router on the other end only speaks half duplex. So we've got a duplex mismatch warning coming at us. So I need to go back to half duplex on there. Conf t int fast 0/1 no duplex full. But what I really want to do, that'll put it back to shared, but what I really want is it to be an edge port, because I know it's not going to a switch. So I'll spanning tree port fast. Show run in fast 0/1. So spanning tree port fast. Show spanning tree. And you can see that it's now an edge port and it's shared. So because it's an edge port, when we're reconverging, we won't block on that port, we won't go discarding on that port, and we won't, and we'll just continue forwarding on that port, which is what we want. We don't want to lose connectivity to this guy. If we go discarding on this port and send out a proposal, the router's not going to respond with anything intelligent. It doesn't know the rapid spanning tree protocol. So we don't want to delay for 30 seconds of connectivity loss to this device every single time we have single time we have topology change somewhere else. So it's essential to set spanning tree port fast on edge ports that go to end hosts. Okay, that's rapid spanning tree.